This lesson will be on exponential equations. We just talked about exponential growth and decay, so just a quick review on that because we want to make sure it fits in this context. Exponential growth is a graph that starts out very closely to the asymptote and then grows from there. This line here, the x-axis, is called the asymptote, and that's in the form of y equals a times b to the x, where a is the initial amount and the b is, if it's greater than 1, it's growth, and then if it's between 1 and 0, then we have what's called decay, where the graph comes down through the axis and then the asymptote is in the positive direction, but the graph goes down and decays at the time. So that's when we have between 1 and 0. That's decay. Okay, so growth, decay is the two types of problems. What you want to do when you do these problems is make sure you do not cross the asymptote, and that asymptote might move up or down depending on if there's a number being added at the end or subtracted. And also you want to make sure you set up an XY table and you get values off of your graphing calculator to plot points to show where these values are. Exponential growth and decay, those are what the graphs look like. Now let's talk about the equations. The equations are where we have a situation where we have a variable in the exponent. So as an example, if we've got, for instance, an equation that has b to the x power equals n, okay, we want to figure out what value for x can we put in to solve that. Now, in these first few examples, what we're going to do is we're going to set up problems where the problems actually can get the same variable on both sides. So here's an example. If we have, for instance, the first example is 3 to the x equals 9. Okay, that's one that we're pretty familiar with. We look at that and it's pretty clear that the only way to get that 3 to the x to become 9 is if we put in a 2. If we square x, we get 9. So that's a solution to the exponential equation. We could have problems where maybe it's not quite so clear. Maybe it doesn't come so quickly. So as an example, we might have, for instance, 6 equals 216 to the x power. Now that one is a little more difficult because we know this is 6 cubed, but how do you put that to a power to get it back to 6? Well, the secret is to write it out with that common base. If we write 216 out as 6 cubed, and check that out on your calculator, 6 times 6 times 6 is equal to 216, 6 cubed. Then what we have is that 6 equals 6 to the 3x power. Now we can think of this as the 6 to the first. If they have the same base on both sides, you can set the exponents equal and solve, and what you get is that x equals 1/3, which makes sense now because the cube root of 216 is equal to 6. So that allows us to solve the equation if we get the same base on both sides. That's the basic outline of how we're going to do these problems. So let me give you a couple steps and kind of a rule for this as we do these. If you have an exponential equation where there's a variable in the exponent, what you want to do to solve that is you want to use this rule where you have, if you've got b to the x power equals b to the y power, that means that x has to equal y. If you have the same base, the exponents are equal. So the steps to doing these problems are, number one, you get the same base on both sides. Okay, Okay, so in this case, we had b and b, so the exponents could be set equal. So second step is to set the exponents equal. And then the third step is then to solve. So let's do a couple examples. We'll do two to kind of help us understand how these work out. So the first problem I want to do is if we've got 7 to the x plus 2 power, and that's equal to 49 to the x. You look at these two and they have different bases. So our first step is we got to get the bases to be the same. Well, we can get this 49 to be a 7 squared. That's the same base as this one. So if I keep this one as it is, 7 to the x plus 2, and we make this 49 a 7 squared, we now have the same base. Let's simplify this side though first. We get 7 to the 2x equals 7 to the x plus 2 power. Now we can set those exponents equal. X plus 2 is equal to 2x. Subtract x from both sides and you get 2 equal to x. Let's check it just to make sure. It looks like we made some progress on this, but let's just check. If we put in 2 here, 2 plus 2 is equal to 4. 7 to the 4th power. If you do 49 to the 2nd power, if you did both those on your calculator, they equal the exact same thing. So it works out. Let's try the next one. Let's try a problem that requires a little more working with those sides to get the same base. We want 9 to the 2x minus 5 power equal to, and we'll put 27 on the other side. Now I can't make, in this form, just with integers, I can't make 27 9 to some power, but I can make both 9 and 27 with a base of 3. So let's do that first. Let's make 3 squared on this side, that's what the 9 is, to the 2x minus 5, and then 27 is 3 cubed. Now I'm going to just remember when this exponent is outside of the parentheses, I bring it in and multiply. So I get 3 to the 4x minus 10 power equals 3 to the 3rd. Now I got the same base on both sides, so we got that first step taken care of. Set the exponents equal to each other. So 4x minus 10 can now equal 3, and we can now solve for x. We got it out of the exponent. So 4x, add 10 to both sides, is going to equal 13, and x then is going to equal 13 over 4. Now that's a more difficult number to work with, not quite as obvious in the original problem, but it works. If you put 13/4 in here and multiply it out and put 9 to that power, it's going to equal 27. So the summary is you want to make sure you take these, look at the two sides, see what common base you can go. Sometimes it means you got to factor one down to a lower base, or sometimes you already have the base on each side. Get the bases the same on both sides and set the exponents equal and solve.